It seems that I arrived during the holiday season. So thank you for being here, even though it's holiday. And welcome online. I was visiting Debo, and that's why I thought, well, why not give a talk? Yeah. So I work on differential privacy and anonymous communication. I guess from most of my different anonymous communication work, you already heard from Debo. That's why I'll just dive right into the differential privacy part. And actually, I would like to build a bridge to crypto primitives. That's why, yeah, this talk is about attacker advantage and tight composition bound for attacker advantage. So going back, why privacy? There was a survey 2010 from 28,000 citizens at the age of 15 or more, at least 1,000 per country in the European Union. And they were asked several things concerning privacy or data protection. And then one of the questions was, is disclosing personal information not a big issue for you? 1/3 of the people said, yes, it is not a big issue for me. What happened? I'm not allowed to let people in. Okay. Then another question was, do you trust companies that hold personal information? And if so, which kind of companies do you trust? 32% said, well, I do trust internet service providers, which is not much, to be honest. 22% said, I trust online services like social media. And yeah, I think 2015 Symantec also did the same again, a similar survey, and there the trust in social media was even lower. Not sure what it is today. So another question was, are you concerned that data is used for unannounced purposes? And 70% said yes. So after that, the GDPR, they used this Eurobarometer for basically the kickoff for the GDPR committee. And then after 8 years, the GDPR was enacted, and now we have a strict data protection rule. But still, these concerns of the people are there. Another question remains, how do we provide useful data processing tools while protecting personal information? Because clearly people are concerned about personal information. If only 33% of people say it's not a big issue for them, then, well, 67% somehow were not able to say it's not an issue for them. So there's evidence that actually people might be concerned or might become concerned soon. But the question is still, what kind of attacker model do we get from this problem statement? Probably in crypto, one is used to get a clear definition and then take that definition where it takes you and see what you can do. But of course, also in crypto, they consider real-world things. Now, if we want to give an answer to this real-world question, we can't go the typical route of the say, a trusted receiver, a trusted sender, and we want to prevent a third party to get any information. Right? That's what encryption, for example, does. What we need instead is to defend against the receiver, but still provide useful information for that receiver, like privacy in database queries. And that is a much harder problem statement. You could even say negligible attacker advantage in terms of computational indistinguishability or statistical indistinguishability is impossible here. Because whenever the data influences the result significantly, you will not be able to get a negligible attacker advantage. The attacker will just be able to guess that some data point was in the data set and get a non-negligible advantage of being right. So that's a problem. That's a problem. So we can also make this more formal and prove this. But the main problem is that the recipient is the attacker and the beneficiary. So you have these competing utility privacy requirements. Privacy means we have to protect people's data against the recipients. Utility means we have to provide this very recipient with useful information. Now, one of the colleagues asked me, are you talking about zero knowledge proofs? Thank you for the question. No, I'm not. Actually, I'm also not talking about SMPC because you have a similar setup in SMPC or in universal composability, where you have ideal functionalities. Like we agree on something that is published and say everything else can be simulated. That means the attacker doesn't learn anything beyond the pre-agreed output. Seems to make sense, right? That's also what happens in zero-knowledge proofs, SMPC, or ideal functionalities. Well, the problem is, if you just take an easy example for SMPC and compute the sum of the wealth or the income of the parties that are involved, you want to hide the income of the parties. At least you want to hide any information that goes beyond the sum of the wealth. But that's a problem. We would still leak the impact of outstandingly rich people like Bill Gates, Elon Musk, Jeff Bezos, if they are part of the sum, right? Now the SMPC definition says, I don't care. We agreed that we will reveal the sum and we're done. But if we would replace this one person, this very rich person, with an average person, then the sum would vastly change. So that is leakage that is not covered by the definitions that we have for SMPC or zero knowledge. So no, I'm not talking about zero knowledge proofs, and I'm not talking about SMPC. Here's another example. For example, zero knowledge proof could be given that a published model, machine learning model, has been honestly trained on a signed data set. And we can do this without revealing any further information about the data set. We could have zero knowledge proofs like anonymous credentials, that there's some authorized party that collected the data. And we can have a zero knowledge proof that proves that it was honestly generated. But such a zero knowledge proof, let's assume that it publishes the model. This would still reveal information about the inputs, even though it's a zero knowledge proof. Because an outlier that was used during training can significantly influence the model. And the zero knowledge property says, well, I don't care. I just don't want to reveal anything that goes beyond the information that is in the published model. Then my zero knowledge property holds. That's fine, that's great. And that's an important building block. I don't want to diminish its value. But it's not everything we need. We need to go one step further. We actually need to also make sure that if this one outlier was replaced by a different data point or just removed, that this impact is protected. Otherwise, there are attacks where you can do a membership, like a training data extraction attack. You can get information about the training data just from the published model itself. So, and that is what I'm talking about. We have to go beyond SMPC, beyond zero knowledge proofs, beyond simulatable security, protect the influence of any single data point in the final result while providing useful results to the very party, and hide information from this very party. Let me give you a few examples. We could ask queries about a database. Like, what's the number of people that had cancer and were treated in Unispital Zurich in 2019? This would be a query that we could do on a sensitive data set, a medical data set, and we would get some response. But if the query issuer is curious, then we have a problem, right? We want to give a good response, but we also want to hide the existence or the influence of single data points. You could, of course, add noise to the result, but then the question, this diminishes the response quality and you have basically utility loss. And then the question is, what's the best trade-off? And how do you even quantify what kind of useful guarantees do you get out of that? Another example is like machine learning, binary classification. Look at this. This could be, I don't know, some machine learning model. If you make it more square, then it could be a random forest. Forest. What you want is you want to have accuracy of a machine learning task, say classification, but you also want to hide properties about the training data, because in particular for machine learning, we need a lot of data. And people might be hesitant to give us this data if we are not able to properly protect that data. So no matter that we compute this entire training in SMPC, and we do not reveal anything about the inputs beyond the final model, even then we have leakage. There are attacks that show that we have leakage. So we need more. You could perturb the training, then you get some wrong classification, and you get utility loss, and then the question is, what is the best we can get? Clearly, you have to somehow perturb the training. You have to approximate the training algorithm. And this is done, and we're also working on this. And if we have time, I would actually like to also show you a little bit of that. But we have to find the best trade-off between utility and privacy. And we can't prove negligible attacker advantage because it is not negligible. By definition, it's not allowed to be negligible. Otherwise, the data would not have been used. Like whenever the data is used in a reasonable manner, then attacker advantage, for a reasonable definition of attacker advantage, will be non-negligible. Because then there's some information in the data, and the attacker can use this information and use this property to distinguish whether the data point was used or not. Another example is anonymous communication. Well, it's hard to hide the flow of data. Probably some of you have experience with that. You could delay the messages and let everybody regularly send dummy messages. Sure, we can do that. But all of this incurs bandwidth and latency overheads. And you can do many more smart things. You can run an SMPC and have distributed point functions like Express does. There's tons of awesome work in that direction, but you always have this utility privacy trade-off. You want to hide the communication of individuals, and you want to have an efficient anonymous communication network. So how do we get this trade-off? And how do we prove something useful about that? Another one is system security. We worked on a system where we had some browser plugin for anonymous, for basically producing cover traffic. And using this cover traffic, we said a web page like Reddit could actually send a JavaScript script that lets people that want to join produce cover traffic, and then this cover traffic could be used by actual users of an anonymous communication network to get something like deniable communication. They could deny that they're actually using the network. They could say, well, I'm just providing cover traffic. So that was the idea. Another problem was you need an additional plugin in the browser to use the system. And this additional plugin incurred a tiny latency delay, a tiny timing attack, timing leakage. Well, but an attacker can measure this delay, and if you use the network long enough, it will eventually learn that you're using it, get very strong evidence. Well, what we can do is we can add random delays to the normal system as well, but that reduces efficiency and also the good put and so on, latency. But yeah, this gives us again a trade-off that we want to look at. Another one is encryption, or let me call it differently, speech pattern recognition. There was a great paper that was from the speech patterns you could, in a Skype call, I think, even though everything was encrypted, the ciphertext streams could be used to actually find out what kind of person was speaking. So these are basically volume-based, not only volume-based, also speech pattern-based fingerprinting attacks. Yeah. But also here, you want to hide the length of the plain text, but still small, you want to have small ciphertext and low delays. You don't want to pad every ciphertext to 10 gigabyte. So the paradigm I want to push for, and it's not that I'm dogmatically for differential privacy, but differential privacy at least tackles some of these problems. Except non-negligible leakage for this part where we have utility privacy competition, where we can't do better, and only allow a limited number of observations. In particular, in practice, what is relevant is privacy under high exposure or realistic exposure. So more exposure of the system and of you using the system or your data being used, the less privacy we have. For example, more queries, less privacy. More complex models trained, less privacy. Longer ACN usage, less privacy. Longer speech patterns, less privacy. So one of the problems I want to talk about here, one of the challenges, is how much exposure can a system tolerate before privacy breaks down? By the way, if you have any questions or any comments or any criticism, just shout and talk to me. So that's what this talk is about. I'll show you a graph now. This is just a depiction. I didn't measure anything for this graph. On the y-axis, you have privacy under exposure. That means this is the maximal exposure before privacy breaks down. And on the x-axis, you have the degree of utility loss. So how much are we randomizing everything to death? And it's kind of a log plot. I mean, the privacy is how many, that's the log space, log plot of the number of observations that you can do. And for the crypto guarantees, we're actually in the strong privacy area. We want to be allowed to do, I don't know, 2 to the 80 or 2 to the 100, to see 2 to the 100 encryptions and still, or 2 to the 80 encryptions and still get reasonable confidentiality properties, secrecy properties. So you want to have poly exposure, in other words. You do not have utility problems for crypto guarantees, but if you do the same for like machine learning or anonymous communication, you will not get any utility. You will have very long delays or very high overhead for all the parties. This will not be helpful. Then we have this acceptable privacy region where you have limited exposure, and that's where differential private machine learning also sits. I'm mentioning that because in the last slides I will talk about that a little bit, if I have time. And what this talk is about is to actually push this utility privacy trade-off. Because it turns out that many ways to quantify the leakage that have been given in the past were untight, and we can give much tighter bounds. And in particular, this allows us to get better utility for the same degree of privacy, or better privacy for the same usefulness. So better utility privacy trade-offs. That's what this talk will be mainly about. And just DPML, differential private machine learning, will be some examples I give in the end. So this is joint work with Sebastian Meiser, and also later on David Sommer joined this line of work. How do we define privacy? Well, probably you've heard already, we're using differential privacy. If we take as an example the counting query that counts the number of, or that gives us the median is bad. Let's take the mean of the patient age for the last 10 years. This is, well, it's kind of a counting query. If we know how many patients we have, it's not a counting query. Let's take as an example the number of cancer patients in 2019 in some hospital. So we have that would be a counting query, right? For all pairs of databases that only differ in one row, we want to hide the information, how many people had cancer in 2019. So if we have that, then one way to achieve differential privacy is to actually add noise to the counting result. And yeah, you would have the real result, which is the real counting query, x of q of x0. And then you would have the lambda, which is the width of the noise. It's a scale parameter of the distribution. And we now have these two output distributions. I mean, of course, you have different pairs of output distribution depending on the query, but you can show that this is kind of a worst case pair of output distributions. So it suffices to analyze the leakage that we have for this one. For example, if you have 0, if the real output is 0 or 1. Important for the privacy analysis is just that they differ in 1. Another question is, how much leakage do we have? And what epsilon delta differential privacy tells you is what you have to look at is this area. Either this area or this area, it doesn't matter, they are the same. And this area is called statistical distance in the crypto literature. It's a particular distance, actually. It's called total variation. And you could write it down as delta of these two distributions. I will later write this down as delta of 0 for this pair of distributions. Differential privacy goes one step further, but for delta equals 0, for epsilon equals 0, this is total variation, or the advantage of attacker in the statistical indistinguishability game. That's where you probably have seen this. So let's take as an example this work that we had on timing leakage from a system. Add random delays to counter timing leakage, and assume we have a worst case pair of distributions over response time. So this is kind of the distributions that we got for our systems. One is system A. The dotted line is, that's probably not right. Let's say system A is the solid line and system B is the dotted line for consistency purposes. And this is then the probability mass function. How much, and what's the probability to get which kind of observation? The x-axis is the timing delay, the observation that the attacker makes. What's the response time? And the y-axis is the probability that we observe this response time. And now pure differential privacy would say an attacker makes an observation, has to decide from which distribution was the observation drawn, from A or from B? And then you basically say, if differential privacy holds, we have to be able to say all observations X and B are at most e to the epsilon times as likely as an A. So for every observation that we have here, the ratio of the probabilities is e to the epsilon, at most. That means observing any single event gives you no definite proof that it was drawn from A or from B. In our example, this means that that system A was used or system B was used, or that somebody is actually using the anonymous communication network or is not using it. It's just providing cover traffic. And if there are distinguishing events, like some delay that cannot happen for one of the systems, you would have distinguishing events, and then pure differential privacy fails, because then the attacker would have a definite proof. In one case, the probability would be 0 that this observation occurs. In the other case, it would not be 0. So that's why people introduced the approximate differential privacy version, where you also have the delta. Probably you've seen this epsilon delta differential privacy stuff. People usually omit this A, so it's just epsilon delta differential privacy. That means still all events X and B are at most e to the epsilon times as likely as in B, and vice versa, except for some rest mass delta of epsilon. And if you want to be picky, this is the way I'm describing this is probabilistic differential privacy and not approximate differential privacy. But for our purposes, there's no point in distinguishing these two. And now for different epsilons, this would look as follows. This rest mass for epsilon equals 1 is just total variation, because, e to the epsilon equals 1, that means epsilon 0. For e to the epsilon equals 4, this would be this rest mass that you see here, this tiny sliver. And typically the delta we're dealing with is 10 to the power of -5, 10 to the power of -9, a pretty low number. As an interlude, let me get back to you. So with the statistical indistinguishability theme, if epsilon equals 0 and delta of 0 is negligible, then we actually have statistical indistinguishability. It's the same definition. We're measuring total variation here, and this is exactly the same as the statistical indistinguishability literature talks about, just to give you some points of reference. Differential privacy just generalizes this. So not only for epsilon equals 0, but also for other epsilons. And if you are a machine learning person, then probably what we do here in terms of x in B is at most e to the epsilon times as likely as to happen as an A. This will, you might know this in terms of Bayesian statistics. I just gave a lecture and they explained, basically what we want to bound is the likelihood ratio. E to the epsilon is a bound on the likelihood ratio. The knowledge gain in terms of Bayesian hypothesis testing. If you don't know, yeah? Yeah, there has to be. Because we usually, let me finish my sentence and then I come to you. So if you're a machine learning person, Bayesian statistics, Bayesian hypothesis testing is basically what we're looking at, and we're bounding the knowledge gain, the log likelihood ratio. That's the factor with which we update our Bayesian, our prior odds. Back to your question, yes, there is actually a version where the attacker is like polybounded, computational attacker, and there has to be. Because usually we combine these differential privacy results with crypto. You would say, this is orthogonal, as I told you earlier. We need those SMPC guarantees. We need the zero knowledge guarantees, but we additionally also need that the result of the computation is differentially private. That means if you use them, you inherit all the computational restrictions, like that the guarantees only hold against computational attackers. Let's assume we have a zero knowledge proof, and that only holds against, only has computational zero knowledge. In that case, and we prove that the published information from the zero knowledge proof is differentially private, for example, the learned machine learning model, then the guarantees that we have here correspond to exactly guarantees against a computational attacker. We can still do these kind of proofs by using something like UC and talking about an ideal functionality and so on. Then in the ideal world, we can do this kind of statistical indistinguishability proof, and then prove that the epsilon delta bounds hold against computational attackers if we go through the simulator. So I can send you proofs where we did exactly that, where we use SMPC and say the result of the SMPC is differentially private. So we inherit all the constraints of the SMPC proof. Yeah, thank you for the question. So now, as I told you, for epsilon equals 0, this is just a total variation. But we can plot an entire epsilon delta graph. Because for different epsilons, we will get different results, right? Here on the left side, I show you the e to the epsilon inflated graph. Let me go back. And the rest mass that remains. Here it is something around 0.5 or so. This is a log plot of the delta. And here is the epsilon, so the exponent of this e to the epsilon. And if we now increase the epsilon, the delta, of course, decreases. In the literature, this is called privacy profiles. We call it epsilon delta graph. This is basically a characterization of the leakage that you have. And I'll come back to this characterization at the very end of the talk. For now, this is basically what we will have a look at. Because when we talk about leakage under continuous exposure, we need this representation. We need to know for which epsilon do we have which delta. In particular, we need to know, so just as a glimpse, if there's tons of delta for low epsilon, or if most of the delta mass is present for low epsilon, and for high epsilon you have very low delta, like 10 to the power of -9, -10 or something, then we know that we will get very good composition results. Something in the delta will increase with O of square root in the number of observations. If there's a lot of mass in the higher epsilon regions, then it will increase more in the order of O of number of observations, so linearly with the number of observations. Otherwise, square root in the number of observations. So what happens under observation? Well, what we basically talk about is R-fold composition, but that's the same as looking at the product distributions. The joint distributions where you have the same distribution over and over, and you have the independent joint distributions. And here, for example, if we set, for our example now, the number of compositions to 8, we would get such an epsilon-delta graph. To 64, we'll get such an epsilon-delta graph. Now, the problem is that for 64 already, and also for 8, this product distribution is infeasible to compute. So we can't actually do that. I cheated. I use the result I'm going to present to you now, and then we get these graphs. But yeah, it doesn't work if you do it brute force. Prior approximations, for example, in CCS 2016, there was an approximation. They were actually not bad, but it turns out they were still pretty untight. So if you compare the epsilons here, we would get much better deltas for the same epsilon. And this is our work. We show upper and lower bounds for exactly this delta of epsilon. And I'll ask later on, what is the application to concrete crypto guarantees? But for now, stay with me in the differential privacy area. What we want to do, the bird's eye view of privacy versus utility is, we want to have, like, as a definition, what is the maximal exposure before, let's say, ln2 equals epsilon and delta is 10 to the power of -4, ADP breaks. What's this R before this breaks? And for our system that I showed you, no utility loss means lower random delays, and high utility loss means higher random delays. And here, unlimited, or it's not unlimited, it's polynomially bounded system exposure would be something like 10 to the power of 14 observations, 4t, and limited would be something like 10 to the power of 5 observations. And we want to go far above the 10 to the power of 5. And by providing better composition bounds, we can show that actually we have much more privacy than we previously thought. In order to understand how to get these tighter bounds, we need a notion called privacy loss. And not only the privacy loss, but also the privacy loss distribution. If we go back to our pair of distributions, then at some point, the ratio between these two densities, probability mass functions, is 1, right? So there's this much mass where the ratio of A divided by B is 1. And then we also have to measure how much mass is there. And if we talk about mass, we only talk about the mass of A so the A distribution. How much mass is there where the ratio is 1.2? How much mass is there where the ratio is 1.6? And so on. How much mass is there where the ratio is 2? And here we also have one area, that's our delta, where the ratio is infinite. We put that in I call it the infinity bucket. That's what goes in the end in the delta. And this delta mass has very bad composability properties. It increases linearly with the number of compositions. But all the other ones that are close to 1, they have very good composition properties. They only increase with the square root of the number of observations. Okay, so what I now showed you is a privacy loss distribution. And it's the one for A divided by B. You get another one if you consider B divided by A. But you can compute one from the other. Basically, the ones that are below 1, the ratios that are below 1, then can be used to compute the dual one, the B divided by A. But please stay with me with A divided by B. In the end, we have to consider both. But for explaining what we do, this is the best. Let's stick to one. So from this privacy loss distribution, we can again compute our delta of epsilon values, our approximate differential privacy values. So remember what we said. All events x and b are at most e to the epsilon times as likely as an a, except for the rest mass delta of epsilon. And this delta of epsilon is what we want to quantify now. So what we have to consider, and we've proven that in our paper, please have a look at that if you're interested in the proof, is it suffices to consider the sum of all, go over all atomic events, if we talk about discrete distributions, and look at the difference of a of x minus the inflated b of x. Please allow me, oops, what's happening? No, it doesn't work. Please allow me to go back and show you this inflated distribution. This was what we had here. For epsilon equals 0, we didn't inflate b at all. For epsilon 0.26, we inflated b a little bit and looked at the rest mass, the yellow one. For epsilon equals 1.38, we inflated it even more and looked at the rest mass. And the formula that we computed here was the sum, so the mass that remained here, after inflating b of x. Make sense? After inflating the dotted line. So we get different rest masses here for different epsilons. You have to go through all atomic events and look at the difference of the inflated distribution and the PMFA. Okay, so now I go back. We want to approximate this very formula. So this is the formula. The difference between the inflated b of x with e to the epsilon and a. You can, just as a side note, you can represent b, of course, like a divided by b. It's just some school math. I will use that, that's why we'll leave it there. So if we look at the privacy loss distribution, this is the reordering of the mass. On the x-axis, you have the ratio between the two density functions. And on the y-axis, you have the mass of A for this ratio. Then we can write, we will get there in a minute. You can write, if you write B as A divided by B, then you can pull A out with distributivity and have A of x times 1 minus e to the epsilon and then A divided by B. And probably you recognize this again. This is the privacy loss. This is the ratio between the probabilities. If I go one step back, here when we computed this privacy loss distribution, we also looked at the ratio. The x-axis was the ratio of the distributions. Make sense? No, we added basically, this is A of Q, is the sum of all probabilities that have this ratio. Now we want to use that. Here you see we have this ratio again. This is called the exponentiated privacy loss. And in the end, we have this, whatever is in the infinity bucket. Right? Whatever, where the ratio is infinite. We have to add that. And what we do now is, if we reorder the sum, then we'll get, we go over all privacy losses. Here we have the A of Q. This is the sum of all the mass of A with this privacy loss. In the denominator here we now have Q. This is exactly the exponentiated privacy loss. And we only look at those Q where that are larger, sorry, this is wrong, larger than e to the epsilon. So that's the picture is correct. You can't see my mouse, I'm so sorry. The picture is correct. If our e to the epsilon is 1.6, we look at this rest mass. And this is just a reordering of the leakage. In particular, in this part, the inflated b to the x is larger than a to the x. So it's fine, we don't have to consider that for e to the epsilon equals 1.6. So now our plan for approximating this delta of epsilon is to upper bound q. Because once we upper bound q, we're fine. If we find an upper bound for q, we can find an upper bound for this expression. So let's do that. What we do is we basically discretize the privacy loss distribution. Because on the x-axis, you have exactly this q, this exponentiated privacy loss. And now we discretize it in exponential steps. I could probably have shown you the log space of that, then it would be a linear interval. Then it would be linear intervals. Here, now we have to show you this exponentially distributed buckets. We take some f, which is our, you can choose this, and depending on what f is, it's larger than 1. If it's 2, then it would double. The bucket width would double every time. Typically, it's 1.0001, something like this. And then you would construct these exponentially increasing buckets and sum up all the mass from the original PLD before composition within these buckets. And now we have an upper bound for the ratio because it's just f of I. Here. So what we do is we sum up all the mass where the privacy loss is smaller than f to the power of I and larger than f to the power of minus I. Because f to the power of minus I would go in the previous bucket. Make sense? All right. So we just discretize this privacy loss distribution. And now I show you how to over-approximate this, this Q, this exponentiated privacy loss. And that is exactly our f to the I. It's an upper bound on this Q. And this is completely computable, what we have here now, is completely computable from this bucket distribution. That's the reason why we call this entire system the privacy buckets. And now the question comes, where is the relation to composition? Well, if you properly look at this, then composition is basically looking at the product distributions. The product distributions are independent draws of the same distribution, independent because for different runs of a mechanism, of an approximated algorithm, you would have independent randomness. So what we have here is, for the product distribution, what's the probability that x1 happens in the first draw and x2 happens in the second draw, divided by the probability that x1 happens in the first draw of B, the distribution B, and x2 happens in the second draw, let's say distribution D. Could also be B. Right? And if we know that the ratio of A divided by B is in this bucket, and so is between f to the I minus 1 and f to the I, and the ratio here is between f to the j minus 1 and f to the j, then we know that for the composition, it's between f to the power of j plus I and f to the power of j plus I minus 2. That is the big trick. We are translating, you can generalize this. We are translating composition to convolution. If you look at the privacy loss distribution, then the composition becomes a convolution of the composition, like the product distribution of the observation distributions, becomes a convolution of the privacy loss distributions because of the very reason that I just gave you. We have to consider all, here for one bucket, we have to consider all combinations of j and I such that the property that I have shown you previously holds. Right? So whenever j plus I, here in this case, equals 2, we have to sum it up. here, this bucket together with this bucket. Oops. This bucket 0 together with bucket 2, bucket 3 added with bucket -1, and so on. And that is basically the convolution operation. And that's the main insight that we had. That composition translates to convolution. And because we can reconstruct the delta of epsilon from the privacy buckets themselves, from the privacy loss distribution, the privacy buckets is an approximation of the privacy loss distribution, we can give an upper bound for delta of epsilon. So now you have some implementation problems because your buckets become larger and larger and larger and larger. So at some point you have to rein in the complexity again. Sorry, I'm running around here. Yeah, so we have to summarize two neighboring buckets. Basically, we square the F. We make the approximation more coarse-grained after a few steps. And then we continue our convolutions again. The space linearly increases, and then we have to rein it in again. Yeah, this is making the approximations more coarse. Well, it turns out an unoptimized Python implementation with 405 lines of codes is accessible here, and David Sommer did a great job implementing this. The computation time was dominated by the convolution. You could use more efficient ones, and there's follow-up work that tries to do that. We used, for numerical reasons, the standard normal convolution of n squared. You could use a fast Fourier transform-based solution. This would be n log n. But we saw that you have to do a lot of work to get numerical stability for the fast Fourier transform-based version. That's why we stick to the normal one. So in total, our implementation is good because you can basically, you have time when you compute the leakage, right? You have 30 seconds is what you need for per convolution operation if you have 100,000 buckets. And because we can approximate the number of convolutions due to the I, something like 2 to the I, we can use repeated squaring. So you first compute 2 to the privacy loss, then you square it, then you have 2 to the 1, then you square the result again, then you have 2 to the 2, and so on. And then we only need logarithmically many convolution operations. And now let me show you some results. So what do we get? There are several other bounds here. The moments accountant is very strong, or the COV bounds, which claim to be tight. So for the system that I showed you earlier, cover up, and only 512 observations, you see the epsilon delta graph. The dotted blue line is the lower bound that we provide, and the red line is the upper bound that we provide. At some point, they diverge because our approximation didn't have enough computation time. But you can make this point go farther, much farther down. And you could also improve the implementation, by the way. Yeah. But we are much better than they, right? So you see here this e to the epsilon on the x-axis, and you have delta on the y-axis in log scale, and we are far below them. For the Laplace mechanism and the Gauss mechanism, these are the standard differential privacy mechanisms. There were already pretty good bounds, but our bounds actually give much better bounds for the epsilon delta graph. And here was something for machine learning. For machine learning, there's this differentially private stochastic gradient descent algorithm that works like a charm for MNIST and some fine-tuning tasks. That one also had an untied estimation, this moments accounted. And here we give a tight accounting for that. And by that, you are able to use less noise when learning your machine learning model and still get the same guarantees. Then we also observed, probably it's not so important, but that Gauss noise is actually more optimal under composition than Laplace noise. This is for the differential privacy community important, what kind of noise to use. We've even shown later on with a numerical optimization, we said, well, do the optimization and then do the composition and show what the leakage is and find the right distribution. as an optimization problem, as a machine learning problem. And there also, what the system output was a Gaussian distribution. So it seems that the Gaussian, we have strong evidence that the Gaussian distribution is close to optimal when it comes to composition. And we also applied this to anonymous communication, to Vuvuzela. Like we get 90% improvement or factor 10 improvement in terms of noise that you need to achieve the same guarantees. There's this Vuvuzela system where they add noise messages to hide metadata leakage. And they used some very untied bounds and said, well, you need roughly 450,000 messages of noise every round. And we said, you get the same guarantees with 45,000 messages every round. And why so many? Because they wanted to have something like 1 million observations. We wanted to let the system run for half a year and still be fine. They assumed an attacker that did continuously observe victims for half a year or something. That's why we have these ridiculously high numbers. But you could also assume a weaker attacker and use less noise messages. Okay, so this is what we did. Feel free to play around with it whenever you encounter different privacy challenges. Well, let me go back. There are some implications for concrete security that are unexplored and that I would like to advertise. Recall when we have epsilon equals 0, then and delta is negligible, we have statistical indistinguishability. Or in other words, we have the delta of 0 quantifies the advantage of an attacker, of the statistical indistinguishability attack. For concrete security, if the privacy loss is small, then delta of 0 does not increase in O of number of observations, but roughly in O of square root of number of observations. I didn't give the mathematical justification for that. There is one, but I will not go down that road. So the question, and let me repeat what the privacy loss actually is. This was the ratio of the distributions, right? The output distributions. You have to identify worst case output distributions and then look at the ratio of the density functions. If there's a lot of mass close to 1, then it turns out the leakage increases with square root of the number of observations. So the question that I would have to the crypto community, can we design crypto primitives such that we have high deniability, so that the privacy loss is high? That means the adversary, whatever the adversary gets as leakage, is not a definite proof about something about the input. Of course, when for encryption schemes, when he guesses the key correctly, then probably you don't have much choice. But even then. But in other systems, when we have leakage, we might be able to improve it by saying that the attacker does not get a definite proof. That we always have deniability and say, well, the input could have been something else. It's just that the probability that it was the input that you are guessing is a little bit higher than the other. So the privacy loss is close to 1. Because if that would be the case, then what we can turn around our view and say, we don't care about the advantage being 10 to the power or 2 to the power minus 80. We only care about how many observations is an attacker allowed to make before security breaks down. So then, even if the advantage is something like 2 to the power of minus 50, we can allow 2 to the power of 40 observations, but we would only increase the attacker advantage by 2 to the power of 20 because of the square root relationship. And that might allow us to construct more efficient crypto primitives. All right, I think my time is up. So I have other stuff, but I would like to end here. Thank you for your attention.